Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will continue our learning on Prosper software, and today's topic is about send control method with wire wrap screen. All right, so now as usual, we start with this tab. All right, and for the fluid description, you can follow me. Oil and water, method black oil, separator single stage separator, no emulsion, disable PVT warning, water viscosity, we will use default correlation, viscosity model Newtonian fluid, flow type tubing flow, well type producer, method none, and you can also type in the user information here and also the user comments, calculation type, predict pressure and temperature in offshore condition. All right, so now we will have offshore case, model, rough approximation, range full system, brine properties correlation, we will use default system. And now the well completion, this is the main thing, type cased hole. And for the send control, you open the drop down menu and we select wire wrapped screen. All right, wire wrapped screen. This is the topic of our video. All right, so for the reservoir inflow type single branch, gas conning, no. Okay, so from here we click done and we will wait for the system to be ready. Okay, now the system is ready. We need to input PVT data. The next step, all right, you can follow me. Solution GOR 800 standard cubic feet per stock tank barrel with oil gravity of 38, 38 and gas gravity of 0.8, water salinity 25,000 ppm, no H2S, no CO2, no nitrogen. For the bubble point pressure, solution GOR, and oil formation volume factor. For example, we will select, open the drop-down menu, standing correlation, and oil viscosity, Bill et al. Correlation. All right. If you have laboratory data, you can perform PVT matching, but I will skip the subject in this video. If you're interested, you can watch my other video regarding the PVT matching. All right, so let's keep it for now. All right, so for other data, leave it as default, viscosity, Newtonian fluid again, no emulsion. Okay, so from here we click done. All right, so from the PVT data section, we will go to the IPR data section. And here in this data section, IPR data subject, IPR data section, the wire wrap skin will be important. All right, so open. And now for this case, we will have Darcy. All right, we'll have Darcy. And in this video, I will show you to create, and in this video, I will show you how to create IPR data model using Darcy equation. All right, with relative permeability. So it will be more important, more interesting, and also to show the well test data. All right, to show the well test data, to plot the IPR with the well test data also, and the send control. All right, so it will be very, very interesting and comprehensive. All right, so Darcy, and for the reservoir pressure, you can follow me. All right, 55,200 with reservoir temperature of 210. Water cut still zero. Total GOR of 800 standard cubic feet per stock tank barrel. All right. And let's start with no relative permeability data first, the reservoir model data. Reservoir permeability, for example, 50 millidarcies, reservoir thickness of 100 feet, drainage area of 500 acres, DHA factor, assuming a circular reservoir, it will be 331.6 with wellbore radius of 0.354, right? If it is not a circular reservoir, you can also calculate the DHA factor by opening this tab. You need to provide the length, the width, distance to site, D1, and also distance to N, D2. All right, but let's leave it for now, cancel. Okay, so from here, we will need to provide the mechanical geometrical skin calculation. All right, so enable Wong Clifford model, no, for this case. And for the skin, mechanical skin, we need to provide with value of 1, for example. All right, okay. And then let's try send control. So here the wire wrap skin is very important. All right. Here the wire wrap skin, which is the main subject of this video, plays a very important role. All right. So you can follow me. For the wire wrap skin, the reservoir thickness is 100 feet. All right. Automatically populated with this data here. All right. And then for the reservoir permeability 50 millidarcies. Okay. And then for the production interval 100 feet. All right. So all the reservoir thickness will be opened, will be perforated. All right. Will be contributing to the production. Wellbore radius 0.354. All right. And screen outer radius, this one is very important. Our base case is 0.28. Outside permeability, we can leave it blank. So you can see the message here, leave blank if formation sand between screen and sand face. So for example, between the screen and the sand face, we have formation sand. All right, so we can leave it blank. But if we know that there is solid accumulation between the screen itself and the sand face, then if you if we understand, if we know the permeability, then we need to input the permeability here. All right. And also for the outside beta, for the turbulence, we can calculate actually, or we can use this default number, all right, that already automatically populated within this feature. Okay. So all done for the send control. Now we need to calculate. Press calculate. All right. So as you can see, our maximum flow rate, the absolute open flow is 27,010 stock tank barrel per day. All right, so that's quite easy. Click done. And let's say if we have relative permeability data and we want to make the calculation even more detailed. All right, so in here, relative permeability data, we open the drop down menu and we click yes. All right, let's check the reservoir model. No change. No change for mechanical geometric skin, but now we have a new tab, which is relative perms or relative permeability. Okay, let's follow me. Residual water saturation, in this case 0.2, for example, with residual oil saturation of 0.2. If you have relative permeability data, core data, of course, right, you can input the information here. And water endpoint relative permeability, in this case 0.8. Oil endpoint relative permeability also 0.8. Core exponent for water, for example, 1.5. Core exponent for oil, for example, 1.5 or maybe 2. All right. And water cut during test, let's keep it 0. And estimated water saturation, for example, 0.2. Okay, so after having this relative permeability data, let's check it out again, the calculation. All right, so as you can see, now we have a more detailed calculation, but the result stays the same. Okay, so it is better actually. We keep the result. There is no change in the result, but now the calculation is more robust, more detailed, more analytical. Okay, so I will keep it like this way. We can click this one, view results for the table. You can copy everything and paste the results on your spreadsheet. And also you can plot the results by clicking this one. Once again, plot results. Okay, done. All right, so now you can see this is our IPR with the wire wrapped skin. Okay, we have pressure on the vertical axis, the flowing bottom hole pressure, and flow rate, right? Liquid flow rate in this case on the horizontal axis. All right, so very easy, very interesting. And lastly, I want to show you how to plot, for example, if we have well test data. Okay, we open this one. Let's say I have 3 points, 3 well test data, 5,000 liquid rate with FBHP, flowing bottom hole pressure of 4,400. And the next data test is 7760 4050 PSIG. And lastly, let's say I have the test data of 10,000 stock tank barrel per day with bottom hole pressure, flowing bottom hole pressure of 3,600. Okay, I can leave the data, I can leave the date or the comment blank. All right, click done. Okay, now again, plot the IPR, plot results, and here plot test data, make sure you select yes. Click done. Right, so you can see we have the IPR, the pink line, and we have well test data here. So you can see the IPR is quite matched with the well test data. Okay, and for example, the data provided, the well test data provided is not really accurate and you want to edit the data, you can do that by clicking here, test data. And for example, we want to make this one correct. So the flowing bottom hole pressure, I think it is 3,700. Click done. All right, it is more matched. All right, so by doing that, you can plot the well test data on the IPR with the IPR. All right, so that's one thing new for us again in this channel. So from here, we can finish this IPR data section, click done. All right, so now you can see the IPR with the well test data. And as usual, we will go to the next section here. We will edit the deviation survey, downhill equipment, and geothermal gradient. Click edit, and you can follow me. This is the measured depth and the true vertical depth, 600, 600. Still vertical axis, 1005, 1000. And then we have 4075 at 4000. And then 7700, 7500. Lastly, the bottom of the well, 9275 at 9000. Okay, you can also plot to see the measured depth against the cumulative displacement. We have a deviated well here. Click finish, click done, and then the equipment data itself. Okay, first we have the Christmas tree at 0 depth or at 600. Okay, and then we have tubing with the measured depth down to 1000 feet with this one as the tubing inside diameter or tubing internal diameter. And then this is the default roughness. We use the default roughness rate multiplier 1. And then we have safety valve, subsurface safety valve, triple S and V with smaller ID. Keep it 1, rate multiplier 1. And then we will have tubing again down to 9,000. The tail of the tubing, the tailpipe, and then we have 4.052, the same roughness. We can keep it that way, rate multiplier 1. And lastly, we have the casing. down to the bottom of our well, casing inside ID 6.4. I keep the same casing inside roughness and red multiplier still 1. Okay, click 1, click done, and lastly the geothermal gradient for the overall heat transfer coefficient 8. This is important for the temperature calculation, the heat transfer coefficient, the heat transfer calculation along the well, along the tubing and the casing, and the temperature at zero depth, 60 degrees Fahrenheit. At the Christmas tree depth at 600 feet, the temperature is a bit cooler, 40 degrees Fahrenheit. And at reservoir level at 9275, the temperature is 210, okay, as imputed in IPR data section, right? So from here, we can click done and we can check the summary by clicking this button, okay, summary in table. Again, you can copy and paste the table on your spreadsheet, and we can also draw down hole. All right. You can see the Christmas tree, the depth in measured depth and true vertical depth, MD and TVD, tubing, subsurface safety valve, tubing, and then casing. All right, so far so good. So from here, we can click done. And lastly, we can perform the nodal analysis. All right. So here you can see the well sketch, the well schematic. And now we go straight to the calculation, IPR and VLP in flow performance relationship and vertical lift performance under the system selection. All right. Now we need to provide the wellhead pressure or the top node pressure. I'm going to input 500 here. Water cut, keep it 0. Total gas oil ratio 800. Standard cubic feet per stock tank barrel. Vertical lift correlation, I will use petroleum experts too. Solution node will be at bottom hole. Okay, so solution node will be bottom node. Rate method, I prefer automatic geometric, right? So that I can catch, for example, if I have unstable zone, I can show that on my IPR and VLP. I can show that on my nodal analysis plot. All right, so we can disallow this one and we can use no here. Okay, click calculate, show calculating data. Done, very easy, right? Very simple. So now as you can see with our configuration with wire wrap skin installed on the tubing, now we can achieve liquid rate of 14,858.6 stock tank barrel per day, almost 15,000 stock tank barrel per day. And now here you can see the pressure drop due to the sand control, pressure drop due to the wire wrap screen, here, 57 psi. Okay, so the pressure drop caused by the wire wrap screen is 57 psi. All right, and you can also show the plot, system plot, plot all cases. X-axis as usual liquid rate, whereas for the y-axis we will show the VLP pressure, IPR pressure, and also of course pressure drop due to the wire wrap screen or DP send control. Click done. All right. So as you can see, there is a change in DP send control where we increase the liquid rate. If I maximize in this section, right, press the left button, hold, and highlight this section. Yeah, you can see there is a linear trend. There is a linear increase, positive linear increase of pressure drop due to sand control if we increase the liquid rate. Okay, click replot. We have the IPR, the orange line. We also have the data, the well test data, this one, these boxes. We have the VLP, the pink line, And we also have the pressure drop due to the wire wrap screen shown by this purple or pink line. All right, click finish. Now, for example, I want to do sensitivity analysis by varying the water cut. What will happen if we have higher water cut? So let's go to cases, select water cut on this drop down menu, and I want to make the water cut from 0%, 20, 30, 40, 50, all the way to 100%, or maybe 95% instead. All right, what will happen? Click done. You see we have 11 scenarios of water cut. Just click calculate, show calculating data. Very fast, right? The calculation. All right, you can see the nodal analysis will change, and you can check the liquid rate. Okay, and also the pressure drop due to send control will also change. All right, we can show the sensitivity plot. Here I plot pressure against the water cut, but the thing I want to show you is the pressure drop. Let's select this one, DP send control, pressure drop due to wire wrap screen, plotted against water cut. Click done. All right, so it's interesting. So by having increased water cut, the pressure drop due to the wire wrap screen will decrease. Interesting. And let's check the plot. Plot all cases. Click done. All right. Okay. So clearly we have different IPR, different VLP, and also the different pressure drop due to send control. And lastly, I want to show you if we vary the outer radius of the wire wrap screen, what will happen? Okay. Now I will make the second scenario. Let's select the outer radius. Which one? Screen outer radius. Our base case is 0.28. Let's say I want to start from smaller screen, from 0.25 in feet to 6 to 7 to 8, our base case, to 9 to 30. And of course, the limit will be the size of the casing. It needs to be smaller than the casing, the ID of the casing. And our casing ID is 0.354 in feet, right? The wellbore radius, the wellbore radius 0.354. So the limit, I want to keep it maximum at 0.32. So far so good. Click done. Again, calculate. You can see the screen outer radius scenarios here from 0.25 through 0.32 in feet. Show calculating data. Right, you can check the results here, the liquid rate, the oil rate, water rate, down to, yeah, many parameters we can get. But the main thing I want to show you is the pressure drop due to send control. So here we can see by having bigger outer radius of the wire wrap screen, bigger screen, the pressure drop will be smaller, right? Quite intuitive. We can plot the sensitivity plot. Yeah, you can see pressure drop due to send control will be smaller if we have bigger screen, all right? And the trend is quite linear here. And again, lastly, we can perform the sensitivity or the nodal analysis, plot, system plot, plot all cases. Done. All right. So by having bigger screen, the IPR changes, but it's not significant. The VLP will be the same. There is no change to the VLP, I think, but the IPR, of course, will change, and also the pressure drop will, of course, be changed. All right, so I think that's all. I hope you enjoyed the video. I hope this video is useful. Thank you so much for watching, and see you again in the next Prosper videos. Thank you.